All right. Hello, everyone. Before I begin this presentation, a little background information about myself and what the presentation is about. My name is Chris Myers. I'm a principal software engineer on Ansible Tower, working on the backend API team, working with the backend API team. I've worked on Tower for the past 5+ years, way back to when we were pre-Red Hat, before we were acquired by Red Hat or IBM. Some features that I'm proud to have worked on include system tracking, which is sadly no longer with us in its original form, and has been converted to the Fat Cache feature in Tower, which I also helped work on. The bundle installer, or the offline installer. The conversion of the task manager to a distributed task manager. Way back, it was Tower used to not have a cluster model and ran on a single node. That was pretty fun converting it to a distributed system. Smart inventory, particularly the host filter. Workflows. And now with Tower 3.7, replacing RabbitMQ with Redis. That was also a lot of fun. So the most recent feature, replacing Rabbit with Redis, that's what this presentation is all about. When a topic pertaining to this work sort of enters the picture, I may delve deeper into that topic, although it may not seem directly related to the topic at hand. But I think the audience that'll appreciate this presentation will appreciate those little deep dives. So without further ado, let's get started. Starting with understanding the current Tower system. So before 3.7, what did Tower look like? What did Tower's usage of RabbitMQ look like? A little bit about RabbitMQ. It's a message broker. There's a lot of, I don't want to call it baggage, but expectations maybe that exist when you call yourself a message broker. And we use a few of those. We set HA mode to all within Rabbit, which in turn causes all of the messages that we send into Rabbit to be duplicated and propagated to all other Rabbit nodes, which in Tower's case is a 1-to-1. So you have a Rabbit node on every Tower node. So when we started to look at maybe replacing Rabbit because of the, as you services folks know, the problems that customers had facing keeping the Rabbit service up, especially with its low latency requirements. So before we started to replace Rabbit, we wanted to understand Tower's use of Rabbit. And in doing so, we identified 3 main types of traffic that flow through Rabbit, or patterns of traffic that Tower uses for Rabbit. The first is dispatcher messages. So the dispatcher in Tower is something that replaced Celery. So if you know Celery, think of the dispatcher as Celery. The types of messages sent to the dispatcher and used by the dispatcher were sort of a command and control type message. So small payloads, structured, almost RPC-like. Some examples of this are locally, we used it almost like an IPC. So the periodic scheduler that would tick every so often to run a node heartbeat, or tick to run the task manager if it needed to. That flowed through Rabbit. RPC payloads for the dispatcher flow through Rabbit. So if you had Tower node 1 running the task manager, and it decided to start job, let's say 37, on node 2, that message would be delivered over the Rabbit message bus, picked up by Tower node 2, and job started. The third use case for the dispatcher is rather than just sort of a directed message, it would issue broadcast message for very particular specific events in Tower, like to reload, configure Tower and Tower settings on all Tower nodes, anything that needed to be globally propagated within the Tower system. All right, so that's the first type of traffic. that we saw in towers, the dispatcher messages. The second are events. Everyone's probably familiar with these. This is what makes up the meat of Tower, is the integration with Ansible and surfacing those events as job events, and that is what produces the standard out in Tower. So they start their life cycle in Ansible as what Ansible calls playbook events in the callback plugin that is set in Runner and now lives in Runner. The callback plugin takes the data structures passed to the callback plugin. For example, a playbook event would be like playbook on start, when there's only one of these for a playbook run, and it's at the very beginning. Another event type is runner on OK, and one of those is emitted for every task for every host. You have a runner on something, where something is OK, changed, failed. And finally, the another event type in this example set is playbook on stats, and that's one that triggers at the very end of a playbook to give you the summary of what happened. So those flow through the runner set plugin, the runner callback plugin in particular. Function hooks are registered, data structures are passed in. That callback plugin converts those data structures to JSON and ships them to Tower. Ships them via another callback. Immediately, Tower puts those playbook events or job events, as they are almost job events now, onto the RabbitMQ. That queue is replicated to all other Tower nodes, and that queue is shared by all other Tower nodes, particularly by the callback receiver processes. So those are just constantly popping off that queue, consuming those events, converting them to job events, and saving them to the database. So this results in a distributed processing that is also durable. All right, third type of traffic that we use RabbitMQ for in Tower are WebSockets. So some systems are set up to sort of shard WebSockets, where with Tower, any client can connect to any Tower node and subscribe to any job, so there's no sharding of WebSockets. The result of this means that all WebSocket events generated in Tower need to be sent to all Tower nodes, because any client could be interested in that job event. Okay. Now we identified the types of traffic that Tower's using. We wanted to start to understand the need for each message type. For dispatcher messages, we know we need a way to get a message from the local node to remote nodes, and it needs to be directed. It also needs broadcast in a few cases. We also noted that we didn't need the robustness of a message bus to accomplish this. At a minimum, we needed something that looked like a socket. For events, we thought we needed to fan them out across the cluster to gain the speed for processing. But when Ryan optimized Tower in 3.6 or 3.7, we saw that the majority of the event processing is actually I/O bound, which we always thought high level, but until we actually did the work to show it, we weren't completely confident in this. But after we showed it's I/O bound, we now know we can process the events locally, and we don't need to distribute them to take advantage of all the Tower CPU cores. The load is really shifted to the database in this case. And then finally, by speeding up these event processings, we found that durability isn't as important as we thought, because rarely now do we begin to build up a queue of event processing. And then finally, for WebSockets, what Rabbit does is really what's needed as far as distribute the messages. So every WebSocket message needs to go to every other Tower node. What isn't needed is the durability in that case. Right, an example of what it looks like for messages to flow through these three different use cases, starting with the dispatcher. So the dispatcher talks directly to RabbitMQ. Node 1 may ask, hey, Node 2, please run job 37, and this is what the flow looks like. It goes into Rabbit. All those messages are propagated across the Rabbit nodes. And then Node 2 is the only one that is concerned with this message, so it pops that message off and does the work needed for it. The second class of messages we have is sort of the broadcast message. In this case, Tower Node 1 is sending out a message for all tower nodes to reload their configure tower and tower settings. So in that case, yes, all the message needs to go to all the different nodes. And those nodes handle that message, restart their services, and reload the configure tower and tower settings. Okay, the life cycle of an event as it's emitted from Ansible and made into a WebSocket, what that flow looks like. Event emits out of Ansible, Tower pushes it into Rabbit immediately. That's propagated to all the nodes, so any node can service that particular event, but only one node will service that event. The callback receiver pulls it in, issues a WebSocket event so that clients can update their standard out live on the Tower UI, pushes it back out to Rabbit, fans it out to all the nodes, and the node for which has clients that are interested in that job event is sent out via Daphne. Okay, so we've covered the background. We know our needs now. Now, what are we going to replace RabbitMQ with? Well, our first inclination was Redis. And after considering some of the clustered setups of Redis, we realized that they just don't fit our needs. I have a separate presentation that has bits and pieces of why that is. And if you're interested, I can go over that with anybody. But we settled on a single node Redis to meet our solution, along with a few other pieces such as Postgres, Listen, Notify, which we'll go over. A little more about Redis and how we're using it. Getting in the weeds, we use a Unix domain socket. First of all, Redis exists standalone on each tower node. It is not clustered. I believe I said that, but I want to reiterate that because people will ask and presume that to be the case. It uses a Unix domain socket for communication. So this furthers the story of, hey, this Redis is local, not meant to be used across the network and shared. The Unix domain socket is both for OpenShift and for traditional VM tower. On OpenShift, the Unix domain socket for Redis, rsyslog, supervisor, particularly supervisor from the web task, is exposed so that the task container can ask the web task to restart rsyslog when configurations change. And that IPC is accomplished through a domain socket. And we switched in OpenShift from TCP ports to domain sockets because it's more secure. Anybody by default in OpenShift can connect to any container and issue commands. And with Redis not being a multi-tenant system with the version that we're using, the only protection might have been a password. So, domain sockets. Let's see. We've added Redis as a container within OpenShift, within the Tower pod, and RabbitMQ is now removed. So that's a little bit about Redis and its configuration. Let's go through the traffic types that we identified earlier, the 3 types, and see what they look like now in Redis. So first of all, events now all flow through Redis, and are processed on the local node only. I'll let that soak in. They are not distributed across all other tower nodes to be processed. Okay. The dispatcher messages go over PostgreSQL listen and notify interface. This is a fairly simple interface that's almost a raw WebSocket. It does have a notion of channels or groups that you can join to get messages. And everybody subscribed to that channel or group will get the message. I like to think of it as a socket.io interface, if you're familiar with using that library in JavaScript. WebSocket. Okay, so next we broke out WebSockets into two use cases, local versus remote. So again, since Redis is completely local, it could not facilitate sending the WebSockets remotely to all of their tower nodes by itself. So locally, WebSockets completely flow through Redis. We use the channels 2.0. We've upgraded to channels 2.0, which uses async, and its default supported connection and store is Redis. So we're leveraging that. For the WebSocket remote case, we are leveraging WebSockets to transmit WebSockets. First, the events flow through Redis. Then the WebSocket events flow through Redis, and they are propagated to every other tower node via these WebSockets. And as you probably know, Tower does not segment or route the WebSocket session, as I explained earlier, amongst the nodes in the cluster. Any tower node can handle any client. So all tower nodes must know about all WebSocket traffic. We didn't try to redesign that that's, I don't know what to call it, property. Something I need to come back and do is create an architectural diagram for you guys. Maybe it's trivial to me at this point, but it's Rabbit replaced with Redis, not interconnected. So if we have any architectural diagrams of existing tower, I'll probably just take Rabbit out, put Redis in, remove some arrows. Okay, we're going to go through more in depth what the implications of switching to Redis to facilitate these three types of traffic. So sort of what's changed, if anything. So the dispatcher messages are now ephemeral versus before they were durable. They would survive reboots and other failure cases. We didn't really need the durability. But you may see, I could see, predict maybe different failure cases that you might see and what they look like. So I'm going to try to describe some of those. Like, for example, jobs may get stuck in waiting for a short period of time. When the task manager decides to run a task, particularly when there's no business logic blocking the task and when there is known capacity to start the job is transitioned from pending to waiting. Then, when the transaction is complete in the database of that transition, a message is sent to the dispatcher to say, start this job, pick this job up. With RabbitMQ, that was a durable message. With Postgres, this isn't the case. So now, not now. There has always been this small time window that this message would not get sent, right? If you save that transition to the database, and you have a crash right after that save, right after that transaction finishes, the job would not get asked to start. And this happened for us when RabbitMQ was in an error state. Tower would transition the job to waiting, and then RabbitMQ wouldn't get the message for the dispatcher to start that job. Now, luckily, we sort of account for this with our Reaper. So after 120 seconds, if a job is stuck in waiting, we will kill that job. And this is still the case. Now, we could deal with this problem. It's basically we have two sources of truth, two data sources that are out of sync. So we could use something like a two-phase commit to make sure these units are in sync. But this is really only a problem when Tower goes sideways, and we have a way to deal with this. Note that in OpenShift, if you're using the container groups feature, we do not have the 120-second Reaper because we rely heavily on OpenShift. We say, hey, OpenShift, please run this container or this pod or this thing. Bring this thing up for us. And we don't know how long OpenShift is going to take. With Tower, we set it to 120 seconds because we can introspect what Tower's doing, and we know that Tower can handle this piece of work immediately. All right, a little more about the dispatcher. A key thing that the dispatcher runs is the task manager. It runs a lot of other important ancillary jobs. The new automated analytics feature, generating the payload for that, the heartbeat, works similar to that. But back to the main thing it does, the task manager. The task manager is a centralized. It makes decisions. It does not distribute the decision making. The first thing it does is grab a lock on a global task manager lock. So no other node is running the task manager while one node is running the task manager. Yeah, we could have designed it where we, only took a piece of the work where we could be running the task manager in parallel on all the nodes. But that's not the case, so it's centralized. Okay, when the task manager decides to run a job, it picks the execution node that the job will run. You can imagine a less centralized job management system in Tower that maybe submits jobs to the instance group, and then maybe there's another heuristic or algorithm for distributing the work amongst the instances in the instance group. For example, you can imagine a round robin as the simplest implementation of that. But that's not super important to this. It's just one of those deep dives. So again, we decide the node that the job will run, what the job will run on. And that's decided by the task manager. Now we need to notify that node that, hey, this job exists and you're going to run it. To do this, we have a per node queue that is simply the name of the node. So in the listen notify of Postgres, the listen part is listening on a queue that is named the instance.hostname minus some characters that Postgres doesn't like, replaced with some other characters. I mention that because if a user maybe names their Tower node something like Tower Unicode character dragon and Tower Unicode character clown, that might be problematic. Yeah, so note that the Postgres listen notify is sort of a broadcast. If multiple connections are listening to the same channel, they will all get the message. So we create this sort of non-shared channel by ensuring that only one listener is listening on a queue, a per Tower node queue in this case. Okay. We do use that broadcast property of listen notify for those needs of tower that are broadcasty, like configure tower and tower settings change, when a project is deleted, cleaning up the on-disk resources across all tower nodes, turning on profile debug. Those are a few that I found in the source code. Postgres related to PG Bouncer. I've heard some customers maybe use PG Bouncer to pool connections. We haven't actually tested that, but we know that this new listen notify usage does require session pooling versus transaction pooling in PG Bouncer. Note that it's always been the case that towers need session pooling because we use advisory locks within tower, and those advisory locks require the session pooling. Okay, what do events look like now that they are in Redis? What does that traffic look like? Our process for pushing and popping events is transparent to the user, but you guys may be interested in the low level, so we'll dive into that. The architecture is still the same on the callback receiver side of tower. It pulls events off the thing, where the thing is now Redis instead of RabbitMQ. Those events are round robin sent to the 4 callback receiver child workers. Note that in that process, there is still a problem, a sort of problem that exists that we've created, where if you restart the callback receiver while processing at high volume, you will lose roughly 4,000 plus events. Those events that are in the queue, 1,000 each for each worker. This isn't an architectural limitation of Redis. If this becomes a major problem, we can solve it through a sort of 2-phase commit where we don't pop it off the Redis queue until we're sure it's in the Postgres database. But this was always the case in Rabbit, and there wasn't a lot of complaints. So that's the same on that side. In 3.7 or 3.6, Ryan reworked the workers to be much more performant. In doing so, events are written to the database in batches. Batches of 1,000 in particular. There's also an optimization where if a worker does not get a batch of 1,000 in 0.1 seconds, then it will choose to flush however many it has. And this is so that in the UI, you don't have an effect where you have job output, nothing, wait 1 second plus, boom, a large amount of output. So there's like a 0.1 second, I don't know what you call it, minimum guarantee that creates a good experience in the UI. Okay, once those batches are inserted, then the callback receiver loops over the inserted batches and emits WebSocket events for them. There was also work done by Ryan to sort of batch the ancillary work that we do for events until the end. And those trigger on the playbook on stats event. So that particular event is going to take longer to process because we have to, one major thing that events have to do from Ansible to Tower is associate the host record in Tower that the event is for. So in Ansible, the event is known to belong to a host by its host name. In Tower, that's a database record. So we need to find the primary key. And we go about that using the host name and the inventory that it ran for. Previously, we were doing that on every job event process. Now, at the very end, we are doing an update, one update to associate the host ID with the event ID. So I talked a lot about the back end of the event processing. The only thing that's changed on the front end, if you will, the part where runner calls to Tower and Tower pushes to Redis, that's where the change has happened. But that's incredibly simple. It's sort of a one-line connect to Redis and call the push command, because Redis is just a key value store where the value is a queue or a list. I've put on here sort of a interaction with Redis CLI. This is how you'd specify the sock file. By default, Redis tries to use the default port. So to debug the, if you suspect events getting backlogged, getting behind processing those events, you want to look at the callback underscore queue within Redis. And this is how you'd introspect that queue's length. In our testing and interaction, if Tower starts to get behind with event processing, it's going to fill up very, very quickly. So normally you may not even observe this key because this key is deleted whenever the queue goes to 0. So if you do observe that queue and it does start getting backed up, Tower's just overloaded. Let's see, I'm looking at some preliminary work that we did and we are doing with the performance team is stressing Tower to see how it behaves when these queues do get backed up. So I'm just going to mention, again, this is very preliminary, but it gives you an idea of what Tower is capable of. We set up a 40 node Tower system. That's 40, which is a lot. We observed just randomly SSHing in and looking. I've seen upwards of 100,000 events per second being processed. That's 100,000 per second. And Googling around, it looks like Postgres is capable of 1 million inserts per second. So we're doing pretty good. Of those, when I SSH'd into view, I want you to note that maybe 40 nodes weren't even busy right then. And it may have only been a few nodes busy pumping out those 100,000 events. When we're not sure if that observation entirely stressed the database or if the database is capable of more at that time. We sort of time box this work, so we won't be, I don't think we're going to explore those limitations anytime soon. However, we are trying to put in place CI to ensure that we don't regress on these performance changes that we've achieved. All right, next up, WebSockets. We're almost done. I think there's one slide after this. How have WebSockets changed with Redis versus RabbitMQ? First of all, we switched to Django 2.0, and we are using Python async. We are using, as I mentioned this before, we are using the supported channels backend that comes with Channels 2.0, which is Redis. And WebSockets are now fully serviced out of Daphne, so the run worker process is no longer needed. You will see a new service called WS Broadcast, and that is the Tower backplane service, which I'll get into. On a single node tower, the WS broadcast service does nothing. Its purpose is that propagation to all other tower nodes. So on a clustered system, the WS broadcast service will propagate every WebSocket message to every other tower node. Also on a clustered tower system, the WS broadcast service will connect to every other tower node, forming a fully connected graph. The discovery of other tower nodes is done through the instance hostname field in the database. It uses the IP or the DNS name, whatever the user configured the hostname to be when they ran the install playbook. Note that in the install playbook, the previous RabbitMQ_host has effectively changed to routable_host. On OpenShift, when AWX_auto_deprovision_instances is set, and Tower sets this automatically for you, Tower will use the IP address of the container instead of the host name. It gets this IP address through the my_pod_IP environment variable. So if you notice WebSockets not getting to other tower nodes and you're on OpenShift, you might suspect that it's getting the wrong IP information for some reason. We have not seen this, but maybe the user has configured the IP address to change or something wacky. There is if you'll remember in Rabbit, we commonly use the management UI to introspect the health and status of Rabbit. The equivalent thing we have now for this WS broadcast service is much like the dispatcher debug interface. So you'll AWX management run_WS broadcast -- status. And the node that you run that on, you will get the status of the connections out to the other nodes. So it may be that you have to run this on a few nodes. If you see a disconnected flag from tower node A to tower node B, then you might go over to tower node B and check the health on that. And if all the WebSocket broadcast connections are disconnected, then you know tower B is unhealthy, or you suspect that it's unhealthy. So this would be a tool. The tool outputs WebSocket events per second, so you can see if maybe one tower node isn't sending or receiving WebSockets at a rate that the other tower nodes are sending. It will tell you the length of the duration of the connection. So if it's like flapping every 5 minutes, 20 minutes, hour, maybe the customer has networking rules that sever those connections. There is a what do they call it? Ping pong heartbeat implemented in these WebSockets, so they will send traffic to try and stay alive. They auto reconnect. That's an expectation you'd probably have. I think it does a exponential back off on the reconnection until 10 or 30 seconds. So if it does get disconnected, it should reconnect fairly quickly. These backplanes auto discover new tower nodes every 10 seconds. In the classic VM tower, this isn't as important because you rerun the install playbook to add a tower node, so all services have to restart. But in the OpenShift case, it is important. If you click and spin up a new tower instance, or you're using, if you spin up a new tower instance, it will be discovered, and all the nodes will connect to that node. Another note here, with Django Channels 2.0, we had to choose a queue depth for WebSocket messages. We chose a depth of 10,000. We reasoned that we chose 10,000 because it kind of relates to the callback receiver. The callback receiver has 4 worker threads. It writes in batches of 1,000, so that's 4,000. We figure we double that number to 8,000 and then add 2,000 for padding. We did observe there is a point where Tower, and in particular here Daphne, cannot keep up with sending out these WebSocket messages. When that happens, you'll note that Daphne is pegged at 100% CPU usage. So even though it is async, there is something in it. There is a limitation here. And when that happens, the WebSocket messages will get dropped on the floor. All right, recapping. From a user-facing perspective, these changes are transparent. But all the things I've listed before still may be useful to the customer through a support lens. All right, we talked about events and how they flow through Redis now instead of through Rabbit and the invocation, specifically that they are now processed on the same node that the playbook ran. The event processing is faster thanks to Ryan's optimizations and inherently Redis. The dispatcher flows over listen and notify in Postgres. Blips on the network can result in task manager oddity, so keep an eye on that. And finally, WebSockets. WebSockets, I don't think I touched on this, but WebSockets need to be configured to align with the Nginx config. Specifically, the protocol, HTTP or HTTPS. So if the user is using a load balancer terminated SSL and it's all HTTP behind the scenes, then the WebSocket broadcast needs to know that it needs to use HTTP. It needs to know the port, and if it should validate the cert. 3 things. I guess those are 3 on-file configurations that need to be set. The 4th thing that needs to be ensured that it's correct is the host name for the Tower node needs to be the instance.hostname in Tower, and it needs to be routable because Tower uses that to discover the other Tower nodes. This was a similar requirement with RabbitMQ. And then know that for the WebSockets, the OpenShift IP will be auto-discovered and used. And thanks to Shane for this work, the OpenShift behaves very similar to the non-OpenShift implementation. That's it. Any questions, you can hit me up on Slack at cmyers.